Okay, so ladies and gentlemen, so welcome to our Math 4427 online lecture again. So today we will try to move on to some further topic related to the Bayesian estimation. Okay, but before that, let us just recall what is the Bayesian estimation. So remember the Bayesian estimation. So start from the case that so you got a random variable, and then we follow certain distribution with some unknown parameter theta. And then in the Bayesian estimation, so we assume that this theta is a random variable. Okay, that is the investigator does not really know the exact value of this theta. Okay, so they only knows that okay the theta has some certain range. Okay, now and then in order to get the distribution of S, remember, so he first tried to make an initial guess on the distribution on the theta. Okay, then this one is what we call what? The polar distribution. Okay, and as I've said, so this will be our initial guess on the values of the theta. Okay, and then we use that and try to obtain my distribution of S through the law of total probability. Okay, now and then after some times, okay, so let's say at time t, then here over this period, so then we may able to observe some actual value of the S. Okay, so let's suppose okay you got a set of data S1, S2, Sn. Okay, be the past observation that you observe over this period. Okay, then using this data, then you are able to update your conjecture on the distribution of theta through the Bayes rule, right? And obtain this what we call posterior distribution. Okay, so which is you obtain through the Bayes rule. Okay, then that will be what our posterior distribution, which is your updated guess. Okay, on the values of theta. Okay, and then last time, so we also mentioned that so depending on the actual observation that you receive, so the resulting posterior distribution may be different. Okay, so it can be something like that, it could be something like that, depending on what kind of observation that you can receive. Okay, and then in last lecture, so we try to go through a lot of example and try to see so how do we get this posterior distribution under different scenario. Okay, so let's say you have complete data or incomplete data. Now and then today, so what we are going to do is so we'll try to look at another aspect of Bayesian estimation, so which is what we call point estimation or interval estimation on the estimator. Okay, now and then let's say so you got a random variable S which follows certain distribution with unknown parameter theta. Okay, now and then here using the sample data, then of course you can try to obtain the updated guess on this theta. Okay, and then of course in some cases, so we may not just interested in looking at this distribution of the theta. So as I have said, so when we study the loss model, so actually what we are interested maybe will be the expected value variance of this parameter of this random variable S, right? Okay, and then as we know before, so whenever which quantity that you're considering, expected value variance or probability. Okay, then of course quite often, so this quantity will be a function of theta. Okay, the value depends on the theta. Then of course if you really want to calculate this value, then what you need to do is then you need to try to make a guess on the values of theta. Okay, so that you can have some number and then you put that in and then you get this number, right? Okay, now so then the question here is, so given this distribution of this theta, okay, which try to listen out all the possible values of theta, then how do you use this to guess the values of theta. Okay, so then this is something that we want to do less. Okay, now then here, just like the parameter estimation, so actually there are two possible approaches to obtain the values of theta. So the first approach is done by point estimation. Okay, that is, so given this distribution, so you try to make a single guess, okay, on the values of parameter. Okay, so that is, so given this distribution, then you try to make this single guess, okay, theta hat, and then use that to approximate the values of theta. Okay, then this is what we call the point estimation. Alright, now but as we know, so besides the point estimation, so another approach is what we call the interval estimation, isn't it? So this try to tell, so under the interval estimation, so instead of asking for the single guess, okay, then we try to make a guess on the range of theta. Okay, I mean the true value of the theta. Okay, and hopefully you want this prediction to be true with some high probability p. Okay, 90%, 95%, or even higher, etc., etc. Okay, so in other words, so you are looking for what? The confidence interval. Okay, now so here in this session, so what we are going to do is, so we will try to look at these two estimation approach in a greater detail and try to see, so how do we make the point estimation or interval estimation on this theta. Okay, now so here, then let us try to start with the point estimation. Okay, now, so under the point estimation, so what we do is, so given an unknown parameter theta, and then we try to guess a value for theta. Okay, that is, you try to pick this single estimate, okay, theta hat. Okay, so that this and so that this one, okay, will be used to approximate the values of the theta. Okay, now then the question is, so how do we make this guess then? Okay, now then of course here, so we have to define, so what we call the good guess. Okay, and then just like the point estimation, so we say this theta hat is a good guess is, so let's say this is the true value of your parameter. Okay, so which is something that you don't know. And then the ideal case is, so we try to choose your point estimator such that this estimated value is close to the true value. Okay, then that will be a good guess, right? Okay, and of course if it is far away, definitely this will be a bad guess. Okay, so that here our good estimator should be what? Should be the one such that the estimated value is closest to the true value. Okay, so then given this, then here our goal will be, we should choose the theta hat such that the distance between theta hat and theta is shortest. Okay, then this is the best that we should do. Okay, now but the problem here is, so in order to choose this estimator, so it looks like that we have to define what is distance. What is the distance between this true value and the estimated value? Okay, so here in order to measure this distance, so we will try to make use of what we call loss function. Okay, so roughly speaking, so the loss function is just simply refer to the distance between the true value of the parameter and your estimated value of the parameter. Okay, and then here, so we will denote it by this L, theta, and theta hat. Okay, which measure this distance, and then this one will be what we call loss function. Okay, now and then here, given this notation, then the next thing is, then we try to build up the formula for this loss function. Okay, now and then here I would say in mathematics, so there are a lot of ways to measure the distance between two elements. Okay, so especially if you are taking the course in topology, so actually there are a lot of different formula that can be used to measure the distance between two parameter in different space. Okay, so here, okay, so here in this session, so I will try to introduce you three popular formula that people use to measure the distance. So the first one is the Euclidean distance. Okay, so which is what the usual formula that we use to measure the distance. Okay, so remember that. So this distance is just motivated from the coordinate geometry. So let's say if you want to measure the distance between two parts. Okay, so remember we can measure this through this formula, isn't it? So you consider the sum of square distance and then you take the square root, right? Okay, so this one, okay, is what we call Euclidean distance. And here in our cases, okay, so we can define this Euclidean distance by the square distance between the actual value of the theta and the estimated value of the theta. Okay, and then you take the square. Okay, so then that will be what we call the square error loss. Okay, so which is as I said, is the common way that people use to measure this theta. Okay, now and then of course besides this, so another distance function that you can try is what we call the absolute distance. Okay, so which is another intuitive formula that we use that we can use. So here then we will define this absolute distance by the absolute value of theta minus theta hat. Okay, just the distance between these two numbers. Okay, we directly measure this. Okay, so then this one is what we call the absolute error losses. Okay, and then the third type of distance, okay, is also popular. Okay, especially if you study the topology. So this is also the distance function that people use. This is what we call CO1 distance. Okay, so basically the idea is, so here if the theta and the theta hat, okay, lie in the same position, okay, then you assign the value CO distance. Okay, otherwise if your theta hat is far away from theta, then you assign the value to be 1. Okay, then this one it will be what we call the CO1 distance, or maybe formally what we call CO1 loss. Alright, and of course some of you may ask, so why do we consider this distance function like that? Okay, now and here just going back to our point estimation problem. Okay, so remember we want to make a single guess on the values of the true value of the parameter, right? Okay, and of course here the ideal case is, so we want to have this theta hat should be 100% reflected true value of the parameter. So that means our ideal goal is the ideal case is, so we will want to have this estimated value to be exactly equal to the true value, and that is the best outcome. Okay, and then otherwise, if the theta hat is different from the theta, actually this theta hat may not able to tell you the true value of the theta, right? And this one will be something unacceptable. Okay, and then because of this, so we can try to define the distance in this way. So if they're the same, then zero distance, best situation. Otherwise, as long as your estimated value is different from the actual value, then this is something unacceptable. Then we assign the distance to be 1. Okay, so here then this is the philosophy of this CO1 distance. Okay, now and then here so we have 3 possible way to define distance. Okay, now and then here let's suppose I try to among these 3 distance, then I try to pick one of that. Okay, now and then here remember in our point estimation problem, our goal is, so we want to choose your estimator such that this estimated value is closer to the theta, right? So that means you want to have you want to choose your estimator such that this loss function is minimized. Okay. All right. Now, but here, so there's one small technicality because in our Bayesian estimation, so our theta is a random variable. Okay, with certain distribution. Okay, remember, we don't know the exact value for that, right? Now, and then knowing that this is a random variable, then of course the actual value of this loss function definitely is unknown. Okay, so here then one fair way to assess the values of this loss function is you just simply take the expected value of that. Okay, that means you are asking for the average distance. And then our goal is we will choose the theta hat such that it minimizes this average distance. Okay, and then here, then we let this minimizer, okay, to be the theta hat star. Okay, so which is the parameter that minimizes this expected value. Then this theta hat star will be what we call Bayesian estimate of this theta. Okay, so which is what the point estimator of the theta that minimize your selected loss function. Okay, now so here then this is how do we do this point estimation? Okay, so we choose the single guess such that your guess, the distance between your guess and the true value is minimized. Okay, now then the question here is, so here so there are three possible choices of this loss function. Okay, then of course depending on the loss function that you consider, then the resulting base estimate will also vary as well. Okay, so it will give you a different number. Now then the next question here is, so given the loss function that you chosen, then what will be the base estimate that looks like? Okay, so here then this is what the theorem 3 is about. Okay, so it try to tell you, so for different loss function that you choose, then what will be the resulting base estimate. Okay, and then here, so this is what this theorem says. So here, given the parallel and or maybe posterior distribution of theta. Okay, so let's say, okay, you got the parallel or posterior distribution. Okay, and then here, this theorem try to tell you the base estimate under different choice of the loss function. And then here, in the first part of the statement, it says if you choose the Euclidean distance, okay, as your loss function, then the base estimate will be the mean of the distribution of theta. Okay, that is the base estimate is expected value of theta. Okay, and then if you consider the absolute distance, okay, then the Bayesian estimate will be the median, okay, of your distribution of theta. Okay, so that means, okay, so let's say this is distribution of theta, then your base estimate will be the median, such that 50% of the data on the left, 50% of the data on the right. Okay, and then the third one is so if you consider the CO1 distance, okay, then the base estimate will be what we call the mole of the distribution of theta. Okay, so remember what is mole. So mole is what is just a single number which you have the highest density on that. So for say, let's say this is the distribution of theta. Okay, then the mole will be the one such that your density function is maximized. Okay, which means it has what the largest. So this is the value which the theta equal to this value with the largest likelihood. Okay, and then here this theorem says that if you choose the CO1 distance, then the Bayesian estimate, the best guess on the values of the theta will be the mole of it. Okay, now so here then this is what this theorem is about, telling you that, okay, so what will the Bayesian estimate looks like for different choices of the loss function. Okay, now then here, then let us try to prove this theorem properly. Okay, now and then here in order to do that, so just recall what is Bayes estimate. So remember the Bayes estimate is what is the point estimator, okay, such that it minimizes the it minimizes this average distance, right? Okay, so here in order to figure out the values of it, so what you need to do is you try to calculate the expected value of this loss function. Okay, now so here then let us start with the Euclidean distance. Okay, that is what? Euclidean distance. Okay, that is L equal to theta minus theta hat all square. Okay, now so here then we first try to compute this expected value. So then given the distribution of theta, okay, whenever it is a parallel distribution or the posterior distribution, okay, then the expected value will be equal to this integral. Okay, so which is equal to equal to expected value of theta minus theta hat all square. Okay, and then this one equal to that by definition. Okay, just this function value multiplied by the PDF of your theta, and then you integrate over all possible values of theta. Okay, now so then once you have this, then that will be the expected distance that we are looking for. And remember, our goal is so we want to choose the theta that minimize this expected value. So mathematically, how do we do that? So then you can try to use the first order condition. Okay, that is you just simply differentiate this expected value and set it equal to 0. Okay, now and here because you only have the theta hat involved in your integral. So to differentiate this, so you can just simply put this thing inside. Put this differential operator inside, and then differentiate the integral. Okay, of course this is just a rough argument anyway. Okay, so here then if you differentiate this, so then this will be something what you get. Okay, and then you set it equal to 0. Okay, and then of course to find the values of the theta hat, so what I do is, so first of all you separate this two integral into two parts, 1 and 2, and because of the theta hat is chosen by you and which is a constant, so you can take that out from your integral. Now then here then this is the formula that you get. Then here first of all for the first integral which is linked to your theta hat, so this one is just what the integral of your parallel distribution over all possible values of theta. Okay, and then because high theta is a probability distribution function, so this integral will be what? The sum to probability, and we know that the sum always equal to 1, so that this integral will be equal to 1, right? And then for the second integral, so that will be the integral of theta times pi theta. Okay, and then this one is actually just what? The expected value of theta. Okay, so given this, then you will have theta hat minus expected value of theta equal to 0. Okay, then you just put this to the right hand side, then you will get the formula of your theta hat, which is equal to what? The expected value of theta. Okay, so that means if you choose the Euclidean distance, then the candidate of your Bayes estimate will be the expected value of theta. Okay, which you evaluate under the parallel distribution or maybe posterior distribution of theta. Okay, now and then of course here you can of course here, okay, so we just determine this Bayes estimate use under this first order condition. Of course formally you should also try to confirm whether it is a true minimizer by considering the second order condition. Okay, so here, okay, just just for the checking, so you can try to differentiate this expected value twice and get the second derivative, and you will find that this second derivative will be equal to 2, which is strictly positive. So that means, okay, so this turning point will be the minimum. Okay, so that's then this will be our desired Bayesian estimate. Okay, so here then this is the proof of the first cases. Now, and then you can also look at the second cases, so which you consider the absolute distance. Okay, so again, to find this minimizer, so the first thing that you should do is you should compute this expected value. Then by definition, so again, this expected value is just equal to this integral. Okay, so your loss function multiplied by the corresponding PDF of your theta. Now, but the trouble here is different from the earlier case. So now your integral involves the absolute value, and definitely this is something not desirable when you do the integration, isn't it? So in order to move on, so you have to remove your absolute value side. Okay, and here just recall from the definition of the absolute value is so this guy, okay, is equal to either this, okay, so if your theta is greater than theta, okay, and then otherwise if theta hat less than theta, which means this guy is a negative, then you reverse this true, right? Okay, so then this is how do you with this absolute value. Okay, and then here given this, then you try to split this integral into two parts like this. Okay, so for the first part, so you integrate this, okay, from theta equal to theta hat up to infinity. So that means it corresponds to theta greater than theta hat. So in that case, so you should take this value. Okay. On the other hand, the second integral will be you integrate from minus infinity up to theta hat, and then here then this will correspond to theta less than theta hat, and then you should choose the first form, okay, for your absolute value. So here by doing this, then you can now eliminate your absolute value side, and you will have two integrals that you need to integrate separately. Okay. Now so here then this will be our expected value of your loss function. Okay, and again our goal is we want to choose the theta hat to minimize this expected value. And again, just like what we did before, then you try to differentiate this average this with respect to the theta hat. Okay, and then you set it equal to 0. Now then to differentiate this function with respect to the theta hat, so the story will be a little bit tricky. Okay, now because here you can see, so your theta hat actually appear in many terms, okay, in your expected value, not just the integral itself, but also the upper part and the lower part here. Okay, so here in order to differentiate this successfully, okay, so especially if you are not good at differentiation, so this is what I do. Okay, so here then let me try to rewrite this integral a little bit. Okay, so we try to further separate this integral, okay, into a couple of small parts. Okay, so let's say for the first integral, then I break it down into two parts. Okay, and then for the second integral, then I do the same thing. And then next, so we will, given this, then we will try to differentiate this function with respect to the theta hat. Okay, now so then the thing is, so for the first integral, so if we differentiate this, so because you only have the theta hat in the lower bound, right? So then that means this one will be equal to minus theta hat pi theta hat. Okay, so you just substitute the theta hat into an integral, but because it appear this theta hat is at the lower mass, so that you have the mass in front of it. Okay, fundamental theorem of calculus. Now and then for the second term, so you first differentiate this term with respect to the theta hat. Okay, then this is something what you get, and then you differentiate this one. Okay, and then you put in the theta hat inside. Okay, and then similarly for the third term, then you also do the same thing. Okay, and then fundamental theorem of calculus. Alright, and then for the last one, so you substitute this. Okay, so here then this is basically what you get after you differentiate this with respect to the theta hat. Okay, and of course here, so we try to set this equal to 0. Okay, now and then here it looks rather complicated, but you can see, so many terms can be cancelled out. So this term can be cancelled out, this term can be cancelled out. Alright, so that here then this is what you get finally. Okay, now and then here for the second term, actually this is what just equal to the probability that your theta less than or equal to theta hat. So this one is just what equal to the CDF of your theta, right? Okay, now and then how about the first term? So the first term is just equal to the probability that the theta greater than theta hat, which is equal to 1 minus probability that theta less than or equal to theta hat. And this one again equal to the CDF. Okay, so here then by doing this, so then this term and this term will be just, these two integral will be equal to these two terms respectively. Okay, so then that will be what the final equation for the theta hat that you obtain. Okay, now so here then so that is the equation of the theta hat, and then of course you can try to solve it. Okay, so you will find that the f theta hat equal to 1/2. So remember this CDF is just equal to what? The CDF, right? Isn't it? Then so here, okay, your theta hat will satisfy that the probability that theta less than or equal to theta hat equal to 1/2. Okay, then what does it mean? So let's say if this is the distribution of theta, okay, so what we are looking for is we are looking for the theta hat such that you have 50% of the data is on the left, and then of course 50% of the remaining data will be on the right, isn't it? Then essentially this theta hat will be equal to your median. Okay, and here then that will be our base estimate. Okay, and of course here in order to verify this is the minimizer, then of course you can always try the second derivative test. Okay, so here, okay, by considering the second derivative test, so the second derivative of this expected value is strictly greater than 0. So that means this median of pi theta will be the true minimizer. Okay, so here then that will be the second. That will be the proof of the second part. Okay, if you try to take the loss function to be the absolute loss. Okay, now then lastly we will try to look at the case if you try to choose the C1 distance as your loss function. Okay, now so in that cases, so then your expected value of your loss function, okay, it's just equal to by definition, okay, just the loss function multiplied by the PDF, and then you sum up over all possible range of the theta. Okay, now and then here so remember for this loss function, so only when the theta hat does not equal to theta, then it takes the value 1. Otherwise that will be equal to 0, right? So here because of this, so actually this summation is just equal to the summation of the pi theta, and you sum up all over the case. Okay, so when the theta does not equal to theta hat, because this one will give you the L equal to 1, right? If theta equal to theta hat, that will be equal to 0. Then that term will be gone. Okay, now and then here, so what is this sum? So remember, pi theta is just what? The PDA of the theta. And then you sum up over all theta, which is not equal to theta hat. Then that means this one just equal to the probability that theta does not equal to theta hat, right? Okay, and then so mathematically, so it can be written as well 1 minus the probability that theta, 1 minus 1 minus the probability that theta equal to theta hat. And then our goal is, so we try to choose the theta that minimize this expected value. And then here according to this formula, we know, so if you want to minimize this expected value, then you should try to choose the theta that maximize this probability. Okay, so that means, okay, so you should choose the theta hat such that this probability will be the largest. Then of course, let's say if this is a distribution of the theta, then your theta hat should be chosen at this point. Okay, such that you have the highest density. Okay, so in other words, this one will be equal to the mole. Okay, so here, okay, then this will be what? The proof, the whole proof of the theorem 3. Okay, so which is try to summarize the base estimate for different choice of the loss function. Okay, now then after this, so let us try to look at some numerical example and try to see, so how do we really get this base estimate under some concrete situation. Okay, so here in this example 38, so we consider this scenario. So let's suppose I got a random variable n. Okay, so which follow the binomial distribution, and then with parameter n equal to 4, and then a parameter p. Okay, so here in this problem, so the p will be your unknown parameter. Okay, and then here, so as usual, so we will assume that the p is a random variable which follow this parallel distribution. Okay, and the p will be running from 0 to 1. Okay, why we have that? Because remember, the p in your binomial distribution refer to the probability of success, so the value must be between 0 and 1. Okay, now and then here, so let us consider this scenario. Now, so let's suppose 1 year has passed, and I find that so there are at least 3 cakes made in this year. Okay, so that means the n1 is greater or equal to 3. So then this will be what? The actual observation. Of this n, okay? And here just remember the n refer to the number of cakes made in a given year. Okay, so here then this will be one observation. Okay, now and then here what I want you to do is, so given this new observation, and you can update your guess on your distribution of p, then what I want you to do is, so I want you to identify, so what will be the base estimate of p that minimize this absolute error loss. Okay, which is this one. Okay, now then in order to do this, so first of all, let us try to think about, so what will be the base estimate looks like. Okay, so here remember, this base estimate should minimize the absolute error losses, right? Then according to the theorem 3, okay, so if you choose the absolute loss, okay, choose the absolute loss, then your base estimate should be what? The median of the distribution. Okay, so then this is what you would expect. Okay, so your base estimate, let's call it p hat, will be equal to the median of your distribution of p. Okay, and here because you have some data available, right? So then that will be what? The posterior distribution. Okay, and mathematically, so this one will satisfy this probability. Isn't it? Okay, so here, okay, then so then this is our target. Okay, now so here in order to use this equation to solve for your p hat, so you have to obtain, so what will be your posterior distribution. Okay, now then to do that, so then we just try to use the base rule and do the job and get your posterior distribution. Okay, now so here I guess I'm not going to go through the derivation of this formula. Okay, you just sustain the base rule that we did a lot before. Okay, and again, okay, just be careful that your given observation is n1 greater or equal to 3, so that your given event should be n greater or equal to 3. Okay, something that you have to be careful. Okay, now so and then the next thing is, so then you try to expand this probability, right? Now and then here I guess for parallel distribution, so this is something, so you can just do the direct substitution. And then the only tricky part is, so how do you compute this probability n greater or equal to 3? And then the story is, so remember, this is a random variable which follow the binomial distribution with n equal to 4. So that means this binomial random variable, it just can only take the value 0, 1, 2, 3, 4, isn't it? And then here, if you are asking for the probability that n greater or equal to 3, so that means it will just equal to the probability that n equal to 3 plus the probability that n equal to 4. Only two choices. Okay, so here then using the PDF of a binomial distribution, so then this is what you get. Okay, so this, the first term we refer to the probability that n equal to 3. The last term refers to the probability that n equal to 4. Okay, given the values of p. Definitely, right? Okay, so here then this is something that you get, and then the next thing is just try to do some algebra and compute the integral in the denominator. Just some tedious calculation. Okay, then you will find that the posterior distribution will be equal to this number. Okay, now then given this, so then the next thing is, then we try to find the p hat by solving this equation. Okay, so here then let us try to do the calculation carefully. Okay, so remember the p hat satisfies this equation because p hat is a median, right? Okay, and then to calculate this probability, just integrate this PDF from 0 to p hat. Okay, and then put in your posterior distribution, evaluate this integral, then this is what you get, and then you set it equal to 1/2. Okay, now and then here, in order to get this p hat, okay, then of course you can try to use the Newton's method. Okay, so just recall for Newton's method, so it is used to solve for the equation of the form f is equal to 0. Okay, so then to use the Newton's method, first of all, you try to define this function equal to the left hand side equal to right hand side. Okay, and then given this, then you try to build up the iteration formula for the p. Okay, and then once you have this iteration formula, then you just choose a arbitrary guess. Okay, and let's take p0 equal to 0.5, and then using this formula, then you can get your iterate. Okay, and then you just keep on iterate this until this number becomes stable. Okay, meaning that it doesn't oscillate. And this limit will be what we call the final solution, right? And then here you see that, so this iterate stop at this number. Okay, and that means what, this number will be the solution of this fp equal to 0. Okay, so which is what, the solution of this equation as well. Okay, so that your p hat will be equal to 0.68863. Okay, so which is our estimate on this p. Okay, so here then this is one example of finding the point estimator of the parameter from your posterior distribution. Okay, now and then perhaps here let's take a look on one more example. Now, so this one will be a little bit harder example. Okay, now so the story is something like that. So let's suppose the chain event in an accident follow the uniform distribution over the interval from 0 to theta. Okay, so here then I let S be the k moments. Okay, and then I know that, so it is it follow the uniform distribution from 0 to infinity. Sorry, from 0 to theta. Okay, and here the theta will also control the range of your random variable. Okay, now and then here just like what we did before, so we assume that this parameter is a random variable. Okay, and then initially, so we assume that so it has this parallel distribution. Okay, and then the theta is greater than 500. Okay, now and then this is my initial get on the distribution of theta. Okay, now and then here let's suppose so sometimes has passed. Okay, and then I realized that in this period, so I got two observations on this came amount. So one is $400, another one is $600. Okay, now and then here given this again, then you can try to use that to update your conjecture on your theta. Definitely, right? And then the question here is, so given this updated distribution, so I want you to give a guess on this values of theta. Okay, that is I want to get this base estimate. Okay, and then I want to minimize this Euclidean distance. Okay, now so then this is what we do. Now then again, just say what we did for the earlier example. So first of all, let us try to see so what will be the base estimate looks like. Okay, now so here because you are trying to minimize the Euclidean distance, and then according to the theorem 3, okay, so which is your first statement. Okay, so then this base estimate will be equal to the mean of theta. Okay, which you evaluate based on the based on posterior distribution. Okay, so here that this is our base estimate. Now then again, in order to calculate this expected value, so the first thing that you should do is again you try to get your posterior distribution of your theta. Okay, that is this one. Now then again, in order to get this, okay, so again you try to use the base rule. Okay, and try to get your posterior distribution like that. Okay, so I guess that this part is still pretty obvious. Okay, now but the next thing is the evaluation of this posterior distribution. Okay, now and here just need to be careful. Okay, now so of course here initially, so we expect that the theta can be any number greater than 500, right? So according to what we got here. Okay, now but here actually, so given this two observation. Okay, so actually this observation will also tell you so what will be the correct range of this theta. Okay, so in particular here, given that your S1 equal to 400 and S2 equal to 600. Okay, so actually this will tell you something about the theta. Remember the theta is what? Is a parameter in this uniform distribution, right? We try to tell you the maximum possible values of S, right? Okay, so that means if your theta is here, then you should expect that all the S, okay, should lie on the left hand side. Okay, and then given this, so immediately you can conclude that first of all, your theta cannot be here. Your theta cannot be here, right? Because or otherwise, okay, so actually it is impossible for you to get this S2. Okay, so here, okay, then given the S1 equal to 400, S2 equal to 600, then your theta must be somewhere on this side. So that means your theta has to be greater than 600. Okay, now so in that cases, so actually this positivity distribution will only run from theta greater than 600. Okay, that is the first thing that you have to be careful. And then another important thing is, so when you calculate the denominator, which is the integral of f times this pi theta from theta equal 500 up to infinity. So again, given that s2 equal to 600, so the theta cannot be less than 600 or otherwise. Okay, so this number, okay, I mean this probability will be equal to 0. Okay, so that means here this integral should run from s equal to 600 up to infinity. Okay, not 500 up to infinity. Okay, so here then this is what you're supposed to get. Okay, and then given this integral, then you just compute this integral and do some algebra carefully, and this will be what our final positive distribution. Okay, now so here after you get this positive distribution, remember, so your base estimate of this theta is the mean of the theta, right? Evaluate under this positive distribution. So here then you can easily get the final answer. Just compute the expected value and use this positive distribution and do the job. Okay, and I guess the remaining calculation is just a very straightforward single calculus exercise. Then you will find that the theta hat will be around 900. Okay, so here then this is just another example of getting this base estimate. So the idea is very simple. Okay, just the same as the earlier example, but just here, because your unknown parameter also control the range of your original random variable s. Okay, so here actually in this example, so you can see, so the actual value of your observation will also affect the range of your theta as well. And then this is something that you have to be careful if you realize that this parameter also control the range of the parameter s. So actually when you calculate the posterior distribution, then this is something that you have to be very careful. Okay, so you first, based on the actual value of the observation that you observe, you first try to come up the correct range of your parameter first. Okay, so remember this, very important. Okay, now so here then actually we finish the point estimation, okay, on the parameter based on the posterior distribution. Okay, then the next thing that we are going to discuss will be, so given the posterior distribution of your parameter, then is it possible for us to use that to find the confidence interval for theta? That means I'm looking for the range of the theta such that this prediction is correct with a relatively large probability. Okay. Okay, so let's suppose if you are able to get these two numbers, okay, A and B, such that this equation is true. Okay, then this interval, then that means, okay, this the true value of the theta will lie between A and B with this high probability P. Then this interval will be a kind of a confident interval for the theta. So because this confident interval will be obtained from the posterior distribution, so we will call this interval will be what we call the 100% credibility interval for the theta. Okay, we try to tell the range of the theta given the distribution of the theta. Okay, now then the next question will be, so how do we get this? Okay, now so in order to get this, so first of all, let us first sketch the distribution of the theta. Okay. Okay, so let's say this is your distribution of theta. Okay, so it can be the parallel one or the posterior, depending on how much information do you have. Okay, and here according to the definition, so our goal is we want to get A and B. Okay, such that the probability that your theta is between A and B is P. Okay, so which is this one, right? Okay, now and then here, just like the case for the confidence interval, so actually there's no unique answer about the choice of A and B. Okay, so here, okay, because your A and B is just need to be chosen such that, okay, your P, your area in the middle is equal to P, right? Okay, then of course we will expect, so depending on the style that you prefer, so you can end up with different confidence interval. So for example, so your confidence, so let's say, okay, if you consider the left tail like this, okay, then your confidence interval will be something like minus infinity up to B, right? Okay, and of course here you can also choose another side. Okay, let's say something like that. Okay, let's say the middle one. Then your confidence interval will be between A and B, right? Okay, now then the question will be, so given so many choices like that, okay, then which one should I take? Okay, now and then here actually to get the this final confidence interval, so just remember, why do we use this why do we consider the credibility interval? What is that? So we want to try to get the range of the theta, right? Okay, now and then here because I want to try to get a good estimate of the theta, definitely we want to have the range to be as small as possible. Okay, so of course here, let's say if I give you the range which is something like this, 3.11 and up to 9.52. Okay, so actually this range, okay, even though you can obtain that, actually it is not quite useful, right? Because so the theta can still have a lot of possibility. Now, but of course, if you end up with the confidence interval like that, then definitely this is a good one, right? Because the range of the theta will be very, very, very small. Okay, and what's more, given this, then you can try to guess the theta will be approximately equal to 6.11. Okay, so that means if you have the narrower confidence interval, so actually it will give you a sharper estimate on this theta. Okay, so in other words, okay, when we try to choose this credibility interval, and our goal is, so we should choose the interval with shortest length. Okay, so just try to make this length of the interval as small as possible. Okay, now and then here in order to get this best interval, then we can consider the S which the pi has the largest density. Okay, because here if you consider this, so even you take a very small interval, so actually the probability that the S is between A and B is already very large. Okay, and here you just try to extend this interval, okay, such that your probability reach the P. Okay, so here then if you consider this region, then your range, then the length of your interval will be what? The shortest. Okay, and then mathematically, so how do we get this? So in order to get this interval, so the easiest way is you try to draw a horizontal line like this, okay, and then you try to lower this horizontal line. Okay, now and then of course here so it will first hit the one with the largest density. Okay, and then if you try to move down, so it will cut this interval. Okay, like in this example, so it will cut at this 2 points. Okay, and then here, okay, then you consider this, then in this region also, then you can find this area, right? Okay, so then which is what the probability that this theta is between A prime and B prime. Okay, and then here, because you are asking, so you want to make this region, the area equal to P, right? Then you just keep on lowering this, okay, until at some point, so this area will reach the P. Okay, then that will be the best interval that we are looking for. Okay, and then here so here, like in this example, so this critical value A and B will satisfy this two equation. The first one is the probability that theta is between A and B is equal to P. Okay, so that is the definition of the credibility interval. Another thing is, so here you can see at A and B, so this PDF, okay, are the same, right? Okay, so that this will give you another given equation for the A and B. Okay, then with this two equation, so you can use that, okay, to find your confident credibility interval. Okay, so here, okay, then this A and B will be what we call HPD credibility set. So here HPD stand for the highest posterior density. Okay, because this will generate the credibility interval with the smallest length. Okay, now so here then this is how do we obtain this credibility, the best credibility interval. Okay, and here I just want to highlight one remark regarding this the derivation of this credibility interval through this approach. Okay, now so here okay, if your posterior distribution happen in this form, okay, which you only have the single a single peak like that, okay, then here and then here, okay, then your credibility interval will be a single interval like this. Okay, now but here in some cases, so especially if you consider some very strange posterior distribution, so then let's say if your posterior distribution may have multiple peak, okay, which is something like that. Okay, now so in that case, then if you try to use this approach to find your credibility set, okay, then it is possible that so your credibility interval may be something like this. Which is a union of three interval. Okay, so let's call it to be S. Okay, and then this satisfies the probability that this theta lies in this set will be equal to P. Okay, so here, okay, just from this example, so you can see, so this credibility interval is not necessary to be the conventional interval that we see before. Okay, so in general, it could be a union of this interval. Okay, if the distribution function has multiple peak. Okay, so that's why here when they talk about this credibility interval, so they will just call it as credibility set. Okay, because also resulting set may not necessary to be the interval. Okay, but nevertheless, whenever it is just a set or an interval, so actually this credibility set will try to give you the range of the theta with the smallest width. Okay, now and then here let us try to look at some example and have a very quick practice on this calculation. Okay, now and then here let's suppose you got a random variable s, okay, and then which follow certain distribution, okay, and then with some parameter theta. Okay, now and then here in this example, so let's assume that so after some investigation of some given data, so I know that the posterior distribution is follow the normal distribution with mean equal to 5 and then the sigma equal to 1. Okay, then what I want you to do is I want you to find out so the shortest 95% credibility interval for the theta. Okay, now and then here to get this, so then we just basically follow this definition. Okay, so we remember, okay, so given the distribution, so we try to find the A and B that satisfy this equation, right? Okay, so here then I try to do that. Okay, now and then here we know, so for the normal distribution, so this is the distribution with a single peak. Okay, so here then what we do is then we just find the A and B. Okay, such that this probability that theta is between A and B is equal to P. And what's more, this a and b, so the density function are the same. Okay, so here then I try to do that. Okay, now so here, okay, to get this, okay, so then you just consider this probability. Okay, now and then here in order to get that, okay, so of course you can try to put in the PDF, okay, and then this is the integral that you are going to have. Okay, now and then of course in order to find the governing equation of the a and b, so what I'm going to do is, so I will try to evaluate this integral. Okay, and then here remember to evaluate this integral involving exponential to the power minus x squared, so we will just use this we will try to use this fact about the standard normal, isn't it? So remember, this integral is equal to this, right, which is equal to the probability that the standard score less than or equal to s. Okay, because this is what the PDF of standard normal. Okay, now and then here this is how do we get this integral? And then of course in order to apply this result to evaluate this integral, so what you do is you try to apply the change of variable and try to transform your integral into the form which is consistent with the integral that I present here. Okay, so I take the z equal to theta minus mu over sigma, then you can transform this integral into this. Okay, and then here for this, so that will be, then for this integral, so that will be equal to this thing minus okay, and then each of this is just equal to this guy. Okay, so that's why, okay, so this is what you get, okay, when you evaluate this integral, and then this one will be equal to 95%. Okay, now and then once you have this, okay, then the next thing is you also need to obtain another governing equation for the a and b, because there are two unknown in this equation, right? Okay, so here in order to do that, then you try to use the second phase that, so at a and b, so your PDF has the same density. Okay, and you just use that, okay, and put in the PDF. Okay, now and here if you try to solve it, then you will find, so a minus mu all square will be equal to b minus mu all square. Okay, now and then of course the next thing is, then you can try to take the square root. Okay, now and here by taking the square root, so you will have two solutions. One is a minus mu equal to b minus mu. Another one is a minus mu equal to minus b minus mu. Okay, now and here so then which one should you take that? Now for the first one, so you will get that a equal to b, but definitely this is something not possible, okay, because we expect so the a and b should be distinct. Okay, so that's the first one will be, you can reject the first one. Okay, and then here then you just apply the second one. So by solving this, then you will get the b will be equal to 2 mu minus alpha. Okay, then that will be the second governing equation for the a and b. And then what I'm going to do is, so I will try to apply this equation, substitute into the first equation here, and eliminate the b. Okay, now then here, then this is what you get. Okay, so put in the b into the first equation, so then you will get this single equation for the a. And then in order to solve this, so let us try to do some simplification on the first term. Okay, and then you will get 3 mu minus a over sigma. Okay, now then the next thing is, so here apparently, so this term are solved different, right? And you cannot do algebra on that. So in order to do some algebra for that, so what I'm going to do is, so I will try to make use of this fact. Okay, so here, okay, if you consider this 3 minus s, actually it can be written as 1 minus 3s. Okay, why? The reason here is, so remember, phi is what? The CDF of a standard normal. Okay, now and then phi minus s, okay, is just the probability that the z less than or equal to minus s, right? Isn't it? So this is what the phi minus s is about. Okay, now and then here, so and then how about the right hand side? So the right hand side is the probability that the standard score greater than s, because this one is what? Probability that z less than or equal to s, right? And then you take one minus this guy and sum to probability equal to 1, then that will be equal to this probability. So that means this will correspond to the region on this side. Okay, now and here, remember, this normal distribution, this is standard normal, right? So that means it is symmetric about the mean, which is equal to 0. Okay, so here, then given this symmetry, so actually these two, these two regions, okay, are essentially the same, okay, because it's kind of mirror image, right? So that these two will be identical due to the symmetry. Okay, and then given this, then you can try to apply this to these cases. So this one, okay, can be written as phi and then minus a minus mu over sigma. Okay, and then you take this one to be s, and then by doing that, then this one can be converted into this. Okay, so that's what you will have two like term, and then you can do further algebra. And then by solving it, so you can get, so the A must satisfy this equation. Okay, then the last thing is, so you just will try to find the A such that this probability equal to 0.025. And then using the normal distribution table, so you'll find that, so this critical value should be equal to, this one I guess I got it wrong. It should be minus 1.645. Okay, because we are asking for this equal to 0.025. So it should be negative number. Okay, sorry about that. So this is a typo. And then here, given this, so the A, so here then you can use this equation to solve for the A. So remember, sigma equal to 1, mu equal to 5. Okay, then you put that in. So this one should be minus, then this one should be 3.345. Okay, and then given this, then you can now use the first equation and obtain the B. Okay, so you just put that in. This one should be 3.345. Okay, then you get the number should be 6.645 for a B. Okay, so here, okay, then that will be the A and that will be the B. So that your 95% credibility interval should be 3.355 and 6.645. Okay, so here, okay, just remind you that, so I guess there's a typo on the second last line here. Okay, so I got, it should be minus 1.645, and A should be equal to 3.345 and B equal to 6.645. Okay, now so here, then this is and then this is just one example of finding this credibility interval. Okay, now and then here, let us try to look at one more example. Okay, now so here in this example 41, so we will try to revisit the example 39. Okay, now so here let me just quickly review what that example is about. Okay, so here in example 39, remember, we consider a k amount, okay, in an accident which follow the uniform distribution. Okay, and then here the theta has the parallel distribution, which is equal to this. Okay, and then here, so given that you have two data, S1 equal to 400, S2 equal to 600, then I can use that to obtain my posterior distribution. Okay, and then according to the according to the result in earlier example, so this posterior distribution is equal to this number. Okay, and then here, remember, the theta will be greater than 600. So due to what? The existence of this second observation. Okay, now and here what I want you to do is, so I want you to find out, so what is the shortest 95% credibility interval for the theta. Okay, now and here in order to do that, okay, so you first of all try to identify what is this credibility interval. Okay, because here remember in the earlier discussion, so your credibility interval, okay, can be either a conventional interval like that if you have a single peak, or you have this multiple peak like that. Okay, so that the interval may be a union of interval. Okay, so here the first thing is, so you first try to determine, so what will be this credibility interval looks like. Okay, now and here so remember this is our posterior distribution, isn't it? Okay, now and here the next we'll try to draw the graph out. Okay, so theta is 600. And then here you take 600, you got 3. Okay, and then here, so this will be what your distribution function. Okay, so here, okay, you can see this distribution. Okay, is not really a conventional distribution like that with a single peak. Okay, so that here you cannot use that two equation to, this two. Okay, so to get your credibility interval. Okay, because it looks like that you cannot have the A and B like this. Okay, now then the question here is then what should be the credibility interval then? Okay, so remember here to find this credibility interval, so we want to find the shortest one. Okay, now even though so this distribution function may not look like the ideal one, okay, but still it has a single peak, isn't it? Now, so here to find this credibility interval, so what I'm going to do is I will just use the traditional approach. So here I try to put this horizontal line, okay, and try to move it down, okay, and here we will try to move down this until it hits some point here, and such that this region will be of the probability P, isn't it? Your target level P, and in our case the P is 95%. Okay, so that here our credibility interval will be from 600 up to A. Okay, so that is the interval that we are looking for, and then we just need to focus on finding this A. Okay, now and then here let us so here I use the B instead. Okay, now and then here to find this B, so I would say this is easy, so you just need to have this probability equal to 95%, right? So that means you are asking for the probability that, so the theta is between 600 up to B is equal to 95%. Okay, remember 600 is your lower bar. Okay, now and then here so this is the things that you need to evaluate, and then here then given this posterior distribution, so put that in, integrated from 600 to B, set it 95%. Then here this integral is not hard to evaluate. Then after you evaluate this, so you will have a simple equation for the B. Okay, and then solving this, so you will find the B equal to 1628. Okay, then combining these results, then you can conclude that the 95% credibility interval will be what? 600 and then up to 1,628.651. Okay, so here, okay, this is just one way of finding the credibility interval. If you find that your distribution may not really follow this pattern, okay, with this single peak, and then you got the A and B at the same time. Okay, so here, okay, so if we encounter this, so actually we just simply follow this procedure. So you draw the vertical, this horizontal line, and then moving down. Okay, and then you move down to some range that, okay, this region become the area of this region equal to your target level. Okay, so this approach works whenever you have this distribution like that, or maybe you have the distribution with multiple peaks as we did here. Okay, so actually both this method will be effective for both cases. Okay, so here, okay, then this is how do we get my interval estimation of the theta using this posterior distribution of your parameter. Okay, so the last thing that I want to say about this Bayesian estimation will be so how do we use the Bayesian estimation to make the future prediction. Okay, now so remember that in our Bayesian estimation, so we start from the random variable s and then following certain distribution with some unknown parameter. Okay, and then here then we try to apply the Bayesian estimation to estimate the parameter. Okay, I mean the distribution of it. Okay, distribution, point estimation, interval estimation, stuff like that. Okay, now but here remember the purpose of doing this estimation, of course, is not just investigate the theta itself, but in fact what we want to do is, so based on our knowledge about this parameter, so we want to estimate the distribution of s. Okay, so what it means is, so let's say at the current time, okay, and then given the data that I get in the past, okay, then using this data, then I try to get the distribution of this theta, right? But what is that for? Of course, I will want to use that to get your distribution of s, right? So that you can use that to make the future prediction. On this s, so that you can use that to estimate the p minimum, loss amount, or stuff like that, right? Okay, now so here the last thing that we will do is, so given the posterior distribution of your theta, so how would you make the prediction of s? Okay, and of course here you can do that, okay, by finding the predictive distribution, okay, which is the distribution of s. Okay, but besides that, sometimes, okay, we may also interest in looking at the expected value and the variance, isn't it? So which are two important so two popular quantity that people will also investigate. Okay, so here then what we are going to do is, so given this posterior distribution, so how would you predict the values of the next observation by considering the mean and variance? Okay, and I would say actually this part is very simple. It just try to make use of what we have learned in the past. Okay, now so here to facilitate the analysis, so let's assume that so we learn the fs s theta will be my distribution of your random variable s. Okay, so that is this one. Okay, and which the value depends on some unknown parameter theta. Okay, now and here given the sets of the observation s1, s2, sn, so you can denote it by this s vector. Then you can define corresponding posterior distribution. So let's call it pi theta s. Okay, so this will be the posterior distribution of your parameter after you get this observation. Okay, now and then let's suppose we have these two quantity available. So what I want you to do is, so I want you to estimate this expected value and the variance. Okay, now so in order to do this, so we start with the expected value. So to do that, so we just use the definition. Okay, so here to compute the expected value of y, then you just derivate using this integral. Okay, so the y times the corresponding PDF. Okay, and of course here, so this PDF in general should be a conditional probability because it is derived given the new this observation. Okay, now and then remember, so how would you compute this PDF? So remember, this PDF actually depends on the theta, isn't it? So here, okay, in order to move on, so we use law of total probability. Okay, so then this one will be equal to maybe I highlight that. So this one equal to this interval. Okay, now so then this is what we get, and then of course the next thing is then we try to evaluate this double integral. And then what I do next is, so I will try to reverse the order of the integration. Now so initially, so you should first integrate with respect to theta and then integrate it with respect to y. But now you try to reverse that, and you first integrate that with respect to y and then theta. Okay, and assuming that the pi and f is sufficiently smooth so that you can do this operation. Now, and then by doing this, so here, then because of the pi does not depends on y, right? Okay, so that you take out from this integral. Okay, so here, okay, to integrate that with respect to y, then you just need to integrate y times fxy with respect to y only. Okay, and here, if you look at this, so this one is nothing but just the expected value of y. Okay, and then so here the y is just same as the x. Okay, and then this, and then here, okay, because this PDF is subject to the assumption that you load the theta. So actually this one actually just the conditional expectation of y given that you load the theta. Okay, now and then here, so and then here, okay, so then this is what you get. Now then what will be this integral is about. Okay, now so here, okay, this is what so remember this is the PDF of theta. Okay, after the updating. And then how about this one? This one is the expected value of y given the values of theta. Now remember when we talk about this conditional expectation, so this conditional expectation actually is just a function of theta. Because the value of this expected value depends on your parameter, right? Okay, so here then this is what you get. And because of this, so actually this interval is just equal to another, so we will equal to the expected value of this functional. Okay, so that here then that will be what the value for the expected value of this future values of this random variable x or maybe y. Okay, and then which is what equal to this double expectation. Okay, so here, okay, actually you can see, so this one in fact is just nothing but just what the double expectation formula. Okay, and here, okay, remember, so the y follows certain distribution, right? And this distribution depends on the theta. So that means the randomness of y depends on these two factors, right? And then to evaluate this expected value. So remember that according to what we have learned in the double expectation formula, so you first try to fix the theta, right? And evaluate this expected value. And then you take the expected value again on the theta, and then you can get the true expected value. Okay, so then here then this is how do you get the expected value of y. Then next we will try to consider the variance of y. Okay, or maybe that is the future value of x. Okay, now and then to do that, so remember, so the variance of y can be computed as the second moment minus the square of the first moment. Okay, so this is the usual formula for getting the variance, isn't it? Now, and then here, in order to move on, so remember, the choice of the y depends on the distribution and also the values of theta, right? So remember, to get this true expected value, then we use double expectation formula to do the job. Okay, so which is something that we deduced that before. Okay, so and then here, okay, we apply that to both cases. Okay, so then we use then this is the double expectation formula. Okay, now and then given this, then what should we do? Okay, so then here, then the next thing that I'm going to do is, so we will try to expand this second moment. Okay, now in here, just recall for any random variable, so the variance of z is equal to the second moment minus the square of the first moment, right? Isn't it? And then if you try to put this to the left hand side, so then this is what you get. Okay, and then here, okay, so I just apply this, okay, to here. Okay, and here just be careful that, okay, because this expected value is conditional on the values of theta, so that both variance and this expected value is also conditional on this theta. Okay, just be careful. Okay, now then this is what you get. Now another last thing is then I will try to separate this two terms. Okay, and in particular here I will try to group this one with the second term. Okay, now and here by doing this, okay, so you can then you can get these two, combine these two together. Okay, now and then here so what is that? So here, okay, you can see, so if you try to treat this expected value of y given theta as random variable, let's call it p. Now because here this expected value depends on theta, and remember in our context, so the theta is also random variable, so that this one is also random variable, right? Now and then here, if you take this one to be p, so this term in the second term is just what? The expected value of p minus the square of p square, okay, minus the expected value of p all square. So this one is just equal to what? Variance of p. Okay, so that's why here then this one will be equal to this guy. Okay, so here then this is what? How do you get the variance of y in this scenario? Okay, so you can try to get it through this formula, and again, so to compute this, to use this formula, so actually what you need to do is to first compute the variance and the expected value of y given that you know the theta. Okay, and then you can get your variance or variance successfully. Okay, now so here then this is how do we get the expected value and the variance of your original random variable s, okay, which is your future prediction using the posterior distribution. Okay, now and here let us try to look at some example and have a very quick practice on that. Okay, now so here in this example 42, so we consider a scenario that, so the king size is, okay, in a Kim event, so it has a exponential distribution with parameter theta. Okay, and here you are also given that, so this theta is a random variable, which with 80% probability, so the theta equal to 8. With 20% probability, the theta equal to 2. Okay, so then that is how you should read that. Okay, now and then here, okay, so let's suppose, so I choose a particular policy from this policy. Okay, so meaning that the theta can be equal to 8 or theta equal to 2. Okay, with this probability distribution. Okay, and here let's suppose for this policy, so I noticed that, so in the past year, so this policy has one claim which is equal to 5. Okay, and then here what I want you to do is, so let's say I want to try to predict the loss amount, okay, the claim size in the year 2. Okay, then I want to look at, so what will be the expected value and the variance. Okay, now and then here in order to get this, okay, so that means you want to get your expected value of y and also variance of y, right? Okay, now and then here let us first call the formula that we need. Okay, so let's say here for expected value of y, then we use this double expectation formula, right? Okay, and then for variance, so you do the same thing. Okay, now then of course here in order to calculate these two, so the first step that you should do is you first try to compute the expected value and the variance given that you know the values of theta. Okay, and then this part is very easy because it follow the exponential distribution. Okay, then from the table, so you can check that the first moment equal to theta, and then the second moment will be theta squared 2 factorial, isn't it? And then of course combining this, so the variance of x, okay, will be equal to second moment minus the square of the first moment. Okay, so which is equal to theta squared. Okay, so that here then you got these two important quantity. Okay, now then given this, then now you can try to calculate this expected value of y. Okay, so here expected value of y is equal to theta. Okay, then this is something what you get. And then for variance, that will be expected value theta, and variance is theta squared. And then plus variance of theta, and then this is theta. Okay, and here just bear in your mind theta is variable. Okay, now so here, okay, then in order to evaluate this expected value and the variance, so the next thing that you should do is you try to obtain so the distribution of theta. Okay, in particular here, given that x1 equal to 5, so what will be the posterior distribution? Okay, I would say this is also very easy. Okay, so here then to get this, so we just simply use the base rule and do the job. Okay, so for any values for theta, whenever it is x or 2, okay, then that is the formula that you can take to get your posterior distribution. And here this f, okay, is essentially the probability that you get the first observation equal to 5 given that you know the theta. Okay, now and here because this is a continuous random variable, so that this probability will be replaced by the PDF, and then you take s equal to 5. Okay, so that this will be what the general posterior distribution, okay, for theta equal to 2 or 8. Okay, and then here so by substituting the theta equal to 2 and 8, then you will get your posterior distribution. Okay, now then once you have this, okay, so then you can easily get your posterior, then you can easily get this the expected value of theta and expected value of theta squared or variance of theta easily. Okay, so for example, if we want to get your, if we want to get the expected value of theta, okay, which you use to find the expected value of y. Okay, so remember the theta can be either equal to 2 or 8, right? Okay, then you just multiply this. 2 times the probability that theta equal to 2 plus 8 times the probability that theta equal to 8. Okay, and you use the posterior distribution. Okay, and then you got these two numbers ready, so you can easily get your expected value. Okay, and similarly for the variance. Okay, so basically you just need to compute these two guys. Okay, now so then so here let's say for the first term which involve the second moment, so then you just apply the same calculation, except that so you consider the theta square only. Okay, then you get the second moment, and then if you want to get the variance, so of course it's also easy, so you just break it down into second moment minus the square of the first moment. Okay, and then these two, so you already get this already. Okay, then you can just put that in, and then you can get your final answer. So I guess I'm not going to go through the calculation because it's just a very messy accounting exercise. So you'll find that for expected value that will be equal to 7.20, and then variance will be equal to 60.1724. Okay, so here this is just a example telling you so how do you make your future prediction using the Bayesian analysis. Okay, so basically it consists of two steps again. Okay, so first of all, you should first try to obtain the posterior distribution of your parameter. Okay, given the data s1, s2, sn. Okay, and then the second thing is, so given the theta, okay, so you try to determine the expected value of s given theta and also the variance as well. Okay, so which are the two key elements in this formula for getting expected value and the variance. Okay, so then given these two elements, then you just and then you just first substitute these these two things, okay, into this formula. Okay, so that's your final expected value, and the variance will be just a function of theta. Okay, and then you evaluate this expected value or the variance using the posterior distribution. Okay, so then this is how we do to make the future prediction. Okay, so here then this is the example 42. Okay, now and here perhaps let's see one more. Okay, so which is a little bit harder example. Okay, so here in this example, so we consider this scenario. Okay, so here in this example, so we consider the claim frequency. Okay, so which is the number of claims in one single year. Okay, and here let's assume that so the n follow the Poisson distribution. Okay, and then with some unknown parameter lambda. And here this lambda, so we assume that it follows the gamma distribution with parameter alpha and theta, which is your initial guess on the distribution of lambda. Alright, now and here let's suppose after some time, okay, and then I got a set of the sample data about the n available. Okay, so let's say this is the n1, n2, and n. Okay, and then let's say, okay, so I know the exact number of claim event. Okay, so let's say this is the claim event in the past n year. Okay, so then this is the past data that I get. Okay, now and here what I want you to do is, so I want you to use this set of the observation, okay, to get this model assumption and try to make the prediction of the claim frequency in the coming year. So in particular, I'm interested in looking at so what is the expected number of claim, which is your expected values of n. Okay, now and here in order to get this expected value, so first of all let us try to get what kind of things that we need to get these values. And then remember, so if your n, okay, it depends on some unknown parameter theta, which is a random variable, so the expected value of n is just equal to the double expectation formula, isn't it? Okay, so you first fix the lambda, get the expected value, and then you take the expected value on the lambda. Okay, now and here so of course the first thing that you should do is you first try to obtain this expected value. Okay, now and here because n follow the Poisson distribution, okay, so that the mean will be equal to lambda. Okay, so that means this guy will be equal to expected value of lambda. Alright, now and then the next thing is just so to get this expected value, then you have to obtain so what is the distribution of lambda. Okay, and more precisely, what we are looking for will be the posterior distribution. Okay, now and here, in order to get this, so remember we can use our lovely Bayes rule, okay, and do the job. Okay, now and here, okay, then this is basically what you get. Okay, and just be careful that here what you are given is the set of data. Okay, so you have n data in total. So that's why here, okay, so you have a Jones distribution. Okay, now but here, because all these data are independent, so that means your joint density can be written as well the product of the individual PDF, isn't it? And then each of these Sn follow the Poisson distribution, okay, with this parameter lambda. Alright, so that here then then this one will be just equal to this product. Okay, and then pi lambda will be your gamma distribution. Okay, so here that will be what our formula for calculating the posterior distribution through the Bayes rule. Okay, now then the next thing is just a little bit painful is you need to try to simplify this expression. Okay, now so here then this is what I do. Okay, now first of all, for the eliminator, so that part is still relaxing. So firstly, so you can first try to cancel out some irrelevant term. Okay, so here first of all you have this factorial can be cancelled out, theta can be cancelled out, and then gamma alpha can also be cancelled out. Okay, because it has nothing to do with the lambda. Okay, and then what's more, so for the numerator, so this one can be combined into lambda times exponential lambda to the power summation of Si, and then exponential minus n lambda, and then combining this with this term here, then you will get your numerator easily. Okay, and similarly you can also do the same thing for the denominator as well. Okay, now and then the next question is just so how would you evaluate the denominator? Okay, and here again this integral is something like lambda to the power something and then exponential to the power minus some constant times lambda. Okay, and then to derive this integral, so remember our usual trick, so we use the trick of gamma function. Isn't it? And then of course in order to do that, then you have to use the change of variable. Okay, this change of variable, and then you transform this integral into the form such that this one is exactly the same as this. Okay, now and then after the transformation, okay, and just be careful on when you do the change of variable, so there will be some constant falling out. So that after this, so then this will be something that you get. And again, this integral is exactly the same as this, so that this will equal to this gamma function. Okay, so this number is just coming from here. Okay, now so here then this is how do you get the posterior distribution. Okay, now given this posterior distribution, then you can now go back to this computation of this expected value. Okay, now and then here to get this expected value, okay, then this is the form, then this is so then this is what you get. Okay, so the lambda multiplied by the posterior distribution, and then you integrate from 0 to infinity. Okay, now and then here after this, then you just put in your posterior distribution, I mean that massive one here. Okay, now and then of course apparently this integral is so complicated. Now but here I would say actually it's not that difficult as you expect. Alright, now first of all, you can first take out the term which is irrelevant to lambda. Okay, so here, okay, so only this term are all relevant to the lambda. Okay, so for other irrelevant member, which is these two, so you can just take that out, let it rest. Okay, and then for the remainder, so you combine them together. Now then this is what you get. Okay, so again, this is of the forms of what? Lambda to the power something, and then exponential, and then times exponential to the power minus something times lambda. Okay, so again, in order to evaluate this integral, then we use this gamma function trait method. Okay, this one. So here then again, I try to use one substitution. Okay, and try to use take the substitution. Okay, and then transform this stuff, okay, into exponential minus y. Okay, so here then after I change of variable, and this is what you get basically. Okay, so again, the thing in the limiter is just equal to the gamma function. Okay, so according to the definition of a gamma function, okay, then this one will be equal to this. Okay, so here then this so then this number, okay, is just coming from this. Okay, and here because you need to have minus 1 in your gamma function, so that you add 1 and subtract 1. Okay, just be careful on this. Now anyway, so after you have this, okay, then this is what you get for the expected value. Of course, you can also do some more work to further simplify this quotient. Okay, because here you can see these two indexes are just divided by 1, isn't it? So then what you do is you use this fact, okay, and then bring down this by 1. Okay, so that this guy will be equal to summation si plus alpha, and then gamma summation si plus alpha, and then these two can be cancelled out perfectly, so that you only have this term surviving. Okay, now and here you can also rearrange the term, then this is what you get finally. Okay, so then here then this will be what the expected value of n, okay, under this posterior distribution. Alright, now and here, so this is what just another example on how do you do this future prediction under the Bayesian estimation. Okay, now and here, just before I stop, so I want to bring out one interesting result, okay, that you can draw from this example. Okay, now so here in this example, so you see, so the expected value of n is given by this formula. Okay, and here what I'm going to do is, so I want to do some algebra, okay, and try to present this expected value into something more meaningful. Okay, so what I do is, so here let me try to define the s bar equal to summation of the si divided by n. Okay, so remember here, this is what the si is my observation, okay, of the ni, okay, which is sample data. So that means, so this thing is just what equal to the sample average of your random sample. Okay, now then given this, so you can rewrite this summation of si equal to n s bar. Okay, now then given this, so this expected value can be written in this form, n times a. Okay, summation si equal to n s bar. Okay, and then the next thing that I'm going to do is, so I will try to split this two terms. Okay, this one and this one. Okay, and break it down into two parts like that. Okay, now and here okay, so after you break it down, okay, and then here then you can find that, so the expected value of n can be written as the sum of these two parts. Okay, now and here in this part, okay, so actually there's something interesting. Okay, first of all, so for the first term it involves the s bar. Okay, so which is what the sample average of s bar. Okay, and then in of your random sample. Okay, and then for the second term, so which is equal to alpha times theta. So what is that? So remember, the n follow the Poisson distribution, right? With parameter lambda, and lambda follow the gamma distribution, isn't it? And then here, let's say, if you don't have any information, okay, so let's say without any information updated, so this expected value of n is just equal to what? The double expectation formula, and then that one equal to lambda, and then lambda has gamma distribution, right? So that means that the mean equal to alpha times theta. Okay, so that means this alpha times theta is just the expected value of n, okay, without any information updating. Okay, so you can regard it as your initial guess, okay, based on your other information. Okay, so here, okay, you can see, so this expected value of n actually can be written as well, the linear combination of this sample average and your expected value of n, okay, of your initial guess on the expected value of n. Okay, and here, okay, so each of these terms is linked by this constant. Okay, and here you can see the sum of these two constants equal to 1. So that you can regard this 2, okay, as a weight you assign to these two quantities. Okay, and here in this formula, you can interpret it as, so given the sets of the sample data, so your expected value of n actually is what? Is evaluated using the sample average, okay, and also your initial guess on your expected value of n, okay, based on other information. Alright, and here you can, and then here, okay, so you can see, so dependence on the values of n, so you will have different weights assigned to these two quantities, and apparently, so if your n is getting larger, okay, so then this weight will be getting close to 1, and meanwhile this constant, the second weight will be tends to 0. So meaning that when the sample size is sufficiently large, okay, so actually you will try to estimate the expected value of n through the sample average only, okay, because here remember, when you estimate the expected value of any random variable, of course the best solution definitely is what you estimate that using your sample average. Okay, remember this is your real data, okay, related to the n, right? Okay, and then here this result confirm that, so if a sample size is sufficiently large, then it will be accurate for you to estimate it using the sample data only. Okay, but here on the other hand, if your sample size is small, which your sample average may not give you a promising estimate on the expected value, then this formula suggests that you should try to estimate together using the expected value of n, okay, which is your initial guess. Alright, so here, okay, then this is just another interpretation of this result. Okay, so in general, when you estimate the expected value of n, okay, then the fair way of doing that is, so you try to use your initial guess on the expected value, which you obtain based on some other information and also some actual data. Okay, and then depending on the sample size, okay, then you put different weights on that. Okay, and the general rule will be, if your sample size is large, then you put more weights on your sample data. Okay, so here, okay, then I guess that then that's all about this Bayesian estimation. Alright, so we try to provide you another approach to estimate your parameter, or how do you make your future prediction. Okay, so then basically we have finished our discussion on this parameter estimation, so which is a very long topic, right? Okay, so let me just briefly summarize, okay, so what we have done in this chapter. So basically, in this chapter, so we try to provide you, so let's say if you got a random variable s following certain distribution with parameter theta, okay, and then here in this chapter, so we try to investigate two ways to estimate this parameter. The first case is, so we just use the standard approach, so we assume that this theta is a fixed number, okay, and then and just we don't know that. Okay, and then here then we learn how to get this estimate this parameter through the method of moments, okay, or maybe more popular on the MLE, okay. And then we also study so how do you estimate the function of a parameter through the delta method. Okay, and then another approach is so we try to do that. You try to estimate this using the Bayesian estimation. That is, so we assume that so the theta is a random variable. Okay, or in other words, so you try to make a guess, okay, on the distribution of theta. Okay, so it can take multiple values. Okay, and then here, okay, so so given the sample data, okay, and then we try to update this conjecture on this distribution using the Bayes rule. Okay, and execute your information updating. Okay, and then of course given this new distribution, then you try to make your future prediction. Okay, so here then basically then this is what we have done in this topic 4, and basically though we have finished the last stage of the construction of the loss model. Okay, then of course after you get your loss model, okay, then of course you can use that to study your Kim frequency, Kim severity, or even the aggregate loss, okay, which we have been discussed, okay, we have discussed, okay, in the earlier chapter. So here then I guess then that's all about this online lecture. Okay, so next time so we will move on to the new topic, which is about the model evaluation and model selection, which perhaps I would say this is the last step of setting up the precise loss model. Okay, so I guess that's all about this today's online lecture. Okay, and have a nice day.